welcome to our 7th meeting of this ASHRAE year. Thanks for all coming out. We're getting close to the end of the year, but I think we've got a great program here for you tonight. So first off, we'll just start by introducing the Board of Governors and the Executive. So we've got Jacob Huff from the Board of Governors. We've got Richard Cameron, who I don't believe is here tonight, Governor. We've got Chris Frawley, Governor. Adrian Matani, Governor. Adam Moons, Governor. Aaron Dobson, our Secretary. Chris Fudge, Treasurer. Our President-elect, Mr. Daniel Redmond. And we've got Abby Saunders, our past president, next to Dan there. And then I'm your president, Adam Graham. So, next up, I'll get Aaron to come up and introduce the guests for the evening.
So we got 13 guests with us this evening. So I'd like to welcome Jason Shottle, Byron Paulson, Scott Ferguson, Brandon Follis, Stephen Menke, Maxine Merker. We also have a visiting ASHRAE Distinguished Lecturer from the UK, Frank Mills, Richard Panton Gerber, Eddie Shuriato, Spencer Fuller, Natalie Therian, Riley Ackerman, and Peter Baird. Thank you.
Thanks, Eric. Definitely great to see a lot of new faces out here tonight. And welcome Frank for coming all the way from the UK to join us. Next up, I'll get Selena up here to welcome some new members.
So the new members that joined the Ottawa-Valley chapter since our last meeting in March are Dr. Bradford Hoover, Kyle Van Woensdijk, Martin Thierret, Puya Kamini, Stephen Croft, and Devin Lake. Welcome to the Ottawa-Valley chapter.
Thank you, Celine. Next up, I think one of the most important things that we do as a chapter for this year, we're going to call up Steve Moons to talk about nominations for years to come. So for what we've got going for next year, and then shaping our chapter for the next several years. So welcome, Steve.
Thanks, Adam. Good evening, everyone. On behalf of Abby Saunders, who was co-chair of the nominations committee with me, to follow up on the opening of nominations at last month's meeting. I'm pleased to announce that we have a proposed slate of executive and board of governors that will provide the leadership for the Ottawa chapter for next year and the roots of the chapter going forward. Before we get to that slate, are there any final nominations from the floor? Excellent. Then if I can have someone motion that the nominations be closed. Anyone? Seconded? Mike, thank you. So for the coming year, the 2018-2019 ASHRAE Ottawa-Valley chapter year, we are pleased to present Dan Redmond to be president. The president-elect will be Chris Fudge. Our treasurer will be Aaron Dobson. And I'm very excited to say that Adrian Matani has accepted the position to move into secretary. Adam Graham will serve ably as the past president as well. On the board of governors, we have Adam Moons, who will be returning to the board. Chris Frawley will be returning to the board. Jacob Huff will be returning to the board. And we bring 2 new people to the board this year, Celine Barbeau and Peter Shawwood. So join me in thanking all of them for the volunteering. Process is going to be at the May chapter meeting on the 15th. We will install the executive of the board, so swear them into positions, and you can all then contact them as you need to get the things done that you need to have done, and it will be your last opportunity to berate Adam. But after that, he's free and clear. So thank you all for your time. Thank you all for your input in getting the nominations put together, and I'm very confident next year's chapter is in very good hands.
I just want to say thank you very much to Steve and Abby for taking over from Bob. Working on those nominations is definitely a lot of time and effort goes in to selecting the right group, and I think you've got the right group for next year. So thank you guys, and congratulations everyone. Next up, I have Joe Del Val somewhere here to talk about Yay.
Hi everybody, just wanted to give you an update. I did say in the communique that it would be on April 26th, the next YA event, and it will be on May 3rd. I didn't have enough time yet to fully book it and kind of start the process of sending out invites, so it'll be on May 3rd, a Thursday, at Tailgaters from about 5:36 until 10:30 or so, whenever people clear out. We're gonna try to incorporate students as well, if there's any students that are still in Ottawa after the school year's done that are looking to network with young engineers in ASHRAE. It'll be a good opportunity for that. So Peter and I will collaborate to make sure we get invites out to everyone. So May 3rd is a Thursday. Maybe have a Jays game that night. Cool. So thank you. Have a good week.
Next up, I was going to call Jacob up, but I'll do a quick wrap up of our seminars this morning. So we had a couple of great seminars. We had DLN from the UK, Frank Mills, talking about cold climate design. Definitely a very interesting topic. Had some great topics that he went over. Next up, we had our speaker for the evening, Emmanuel, forgive me if I get this wrong, Moratendis, spoke about acoustics and went into some detail about different products and system selections for acoustic mitigation. So definitely thank you guys for coming out, and we really appreciate it. And I'll take the opportunity just to invite Frank up here just to present him with a gift for the seminar. Next up, we've got Jacob Huff up here to talk about our technology awards for the year.
Good evening, everyone. So the ASHRAE Technology Awards are here to promote and give some praise to some projects locally that have shown innovative engineering design or any steps in sustainability. So this year's winners, we have 3 winners from the chapter level. So I'd like to thank everybody who did apply, and we'll be taking applications for next year after the summer. So first, in the existing educational facilities category, for his work on Herzberg renewal, I'd like to call up Dan Redmond from Carleton University. Second up, and I don't believe he's here tonight, for the work on the CMHC National Headquarters C building from the other institutional category, Martin Ma from JP2G. I think Mike is here, might be able to take the award on his behalf. And lastly, Patrick St. Oge from BPA. I'd like to congratulate all of our winners, and I look forward to Patrick St. Oge and the HOR project as it will be submitted to ASHRAE region, and hopefully pass through region and on to beyond. So congratulations to all our winners.
Thank you, Jacob, and thank you to everyone who did submit an application to be considered for the Tech Awards. I think we've got a lot of great projects that go on in the Ottawa area, and I do think we could have some of those projects go all the way up to society and win some awards. So definitely a good opportunity. So I'd encourage you next year to get your submissions in. Thank you. Next up, I'll just give a quick overview on ASHRAE Golf. So this year we've got registration open for people who have registered in previous year for ASHRAE Golf. The date is June 4th, and the official invitation or opening for everyone to register should be going up next week. So keep an eye out for that. There should be more details in the next communique with all of the information. Just wanted to make sure it's on everyone's radars. Looks like it'll be another great event. It'll be at the Marshes, and it's a noon shotgun. So look forward to seeing you guys there. Next up, I'll get Chris Frawley to come up and just give a brief overview of the Ottawa Regional Science Fair, which a couple of the board members attended.
Okay, thanks. So one of the things with the science fair is that it's been going on for over 50 years. That's an incredible run kind of thing to have it go that length of time. I actually remember going to something in the Science and Tech Museum years ago. This one was held in Carleton. And the day I went there, it was packed in terms of the parking lots were just overflowing. So to have that many people interested was incredible. It also went over grade schools as well as high schools in terms of the teams that were there. And the fellow that was running it when the awards were given out, I couldn't help but think of some little red squirrel. He was just kind of moving, and he was going to be done by 1 o'clock, and he just kept pushing and pushing. It was like a three-ring circus in terms of the call names down and then come forward. Others were getting their awards, others were getting their photographs, and just kept kind of going in that round circle. So he was pretty good at managing things. For the students that ASHRAE awarded prizes to, the third place was Shrink the Footprint. And it was two young ladies, Angelica Bohm, Mackenzie Watson, an experiment testing the effectiveness of low-E window coatings. And what we were trying to do is find things that were sort of similar to the construction industry to try to foster these people wanting to go into that industry. Second place was passive solar adaptations for houses. And it was two young ladies, Camille Arsenault and Tia Jones, experimental testing different attributes of the solar house, orientation, type of window, paint colors, etc. The one that we found most interesting about her was a young lady in 8th grade, and she was competing all alone. She wasn't a team. Third place, fiberglass insulation is the best choice. And Hannah an experiment testing the effectiveness of different insulators and hot water containers. And she had all these different experiments kind of going on in terms of checking it. But what became interesting is that when it came time to present the awards, we were the first ones up in terms of A for ASHRAE. So they had to change the scenario. So we had all these girls, there were many of them, 5 of them, but all came down exactly at the same time. And so you're wondering, okay, who are you? And then getting the checks from the person who was running it, getting the checks into the right person's hand. It was a lot of fun, but it was very interesting in terms of how they ran it. Anyway, thanks a lot. But just get one more thing. Algonquin College last week had a career fair, and it was kind of a meet and greet thing for the construction industry and students to meet with people in the construction industry. And it was held at the ACE building. It was a fabulous turnout, a lot of companies, a lot of similar to our career fair in terms of booth setup and whatever. But I encourage other people next year to kind of participate in that, because we want to have these people consider continuing in the construction field and replacing the few of us that might be getting a little older. Thanks a lot.
Thanks, Chris, and thank you to Jacob for also going and judging those submissions. Next up, I'll get Dan Vivian up here just to talk about a upcoming event that the PEO has been setting up, and ASHRAE is going to be sponsoring as well. So he'll talk to you about it. It's coming up in early May.
It's really interesting. Chris had just mentioned about the science fair. This event that we have is kind of putting science to the real field, right? So we have an event, we're organizing it, first time, a joint event between ASHRAE and the PEO. We're going to have a field trip to a passive house and a high performance building. The passive house is EcoGen, it's in Merrickville. The high performance building is Sola, it's the warehouse office building for Sola City. So of the interest, like these things are showcasing the highest level of technology performance for HVAC, for building performance. So EcoGen is a passive house. It's located very close to Merrickville. High performance insulation on the exterior, R70, passive solar heating, passive solar PV generation, high performance radiant floor heating, HRV, hydronic thermal energy storage, and of interest, I saw the house last June. It was part of the Green Energy Open Doors when I was there. He's got a hydronic recirculation pump that draws only 23 watts. 23 watts for a hydronic recirculation. That's 0.023 kilowatt. So the house is cooled with 43 watts, is what he was saying. 43 watts. That's half a 100-watt light bulb is what he's using on an extra cool house. Sola City is a 10,300 square foot high performance office warehouse building that supplies solar PV products to Eastern Ontario. Its features include high performance insulation, it's a straw bale construction, passive solar heating, solar PV generation, radiant hydronic floor heating and cooling. So when I was there, I said, cooling? How do you cool with the floor? And he said, we just don't bring it down below condensation point. But he said, by accident, I brought it down below condensation. I brought it down so low, this was in the summertime, that he actually created ice on the floor. So it's really an interesting building. It's 10,300 square feet. And here's the performance on it. It generates 2.5 times more energy than it uses. 2.5, that's 250% more energy. So we're doing a field trip on this. It will be on May the 5th. It'll be 1 o'clock. We're organizing a bus trip for it. And unfortunately, because of the logistics, it will take all afternoon because these places are located in Merrickville and Kempville. The Sola City's in Kempville. So it'll be 1 o'clock till about 6:15 when we actually get in. It's kind of bad news. The good news is the PEO is supplying snacks and drinks. The bus will be supplied between the PEO and ASHRAE. So there will be an Eventbrite sign up for it, and there will be e-blasts from both ASHRAE and the
encourage you to sign up when that event gets put out. Next up, I'll get Mr. Redmond up here to do a quick RP update and tell you all where he's at and solicit some more tickets here.
Tell you all where I'm at. The cat might be out at the what's on the screen here. Thank you very much, Adam. Just very quickly, a quick overview of ASHRAE RP research promotion. This really is the mechanism by which ASHRAE generates funding to further development of the standards and guidelines. And every year, ASHRAE generates this funding by establishing these goals. There are goals for society, there's goals for the regions, there's goals then that are handed down to the chapters. Our goal this year was $30,100, and I'm excited to tell everybody here that we've actually met our goal. We met the goal early. Normally we would be aspiring to reach this in June. And thank you very much to the fantastic support from you, our membership, and the hard work of the RP campaign team. On the team we have Adam Graham, Abby Saunders, George Mamari, Frank Van, Mike Swain, Rob Lefebvre, and then myself as the RP chair. Now, on one hand, it's fantastic that we've met our goal, we've met our commitment to our region, but we are still generating funding. I am still raffling tickets tonight because we have another initiative here in the Ottawa-Valley chapter that we are trying to move forward, and that is a scholarship that it is our goal, and we put this into motion 2 years ago. It is our goal that in the next 3 years, we will actually be able to award a $3,000 per year scholarship to a young student coming into the HVAC in our industry. It's an industry that I think everybody in this room can agree has benefited them greatly, and it's an industry that warrants further development into the future. So I am raffling tickets tonight. We are raffling 4 tickets that were graciously donated by Ainsworth, and the tickets are for field level seats to the May 31st Ottawa Red Blacks versus Montreal Alouettes football game. So if you haven't donated yet, the tickets are 5 tickets for $20. And there are 4 tickets. So just so you know, if I sell you tickets, those aren't guaranteed. This is a raffle. But if you haven't donated and you wish to, please try to get my attention, and I'll come over and be more than happy to accept your support of ASHRAE Research Promotion. So thank you very much, everybody, and thank you very much for the support that you continue to give. Thank you.
Thank you, Dan, and congratulations for hitting that so soon. That really is a testament to the quality of members that we have and the amount of donations that we've received from all of you. So thank you very much for continuing to support us, and look forward to meeting that scholarship, getting it fully funded, and awarding that first one. Next up, we've got tabletops for the evening. So we've got S&P ventilation. We've got Tim Sutton here if he wants to come up and just speak a few quick words on his product.
Thank you so much. My name is Tim Sutton, and I live here in Ottawa. I'm a sales manager for S&P Canada. We manufacture a full line of ventilation products. Tonight we have some of our AC products here. All of our products are AMP certified and CSA approved, so we sell our product through ASHRAE here to the mid-spec market. And if anybody has any questions, we'll be here with the tabletop after the celebration. Thanks.
Thank you. And next up, we've got Master with a couple of tabletops. So I'll get maybe Chris Fudge to come up and tell you all about it.
Hi guys, Chris Fudge, Master Group, we're the representative of York. Tonight we're featuring the York ZD chiller, low pressure, centrifugal chiller available from 165 tons to 1,000 tons. The unit is extremely efficient, let's say, full load kilowatt per ton of 0.48, IPLV of about 0.28. If you're familiar with chiller efficiencies, those are pretty well compared to what I'm used to anyway. I'm kind of showing my age a bit. But and again, extremely quiet and questions about it, please contact either myself, your master representative, or we'll be hanging around a bit afterwards to answer questions as well. And I'm going to ask Adam Boones to come up for talk a little bit about BAW.
Thanks, Chris. Here as a master representative as well, with VAW Systems, full complement of sound solutions, noise abatement. We're going to be here all evening. Emmanuel is going to be speaking as a program speaker this evening. And if you have any questions, by all means, reach out to myself at Master Group or speak with us at our booth afterwards. Thanks.
We were going to do a quick discussion on technical committees. I think what we'll do now is just take a quick break. We'll get some food at the buffet, and then we'll have about a 5-10 minute talk on technical committees before we start with the evening program. So, thanks.
All right, good evening, everyone. My name is Nick Lee. I'm a global product manager with Nortec manufacturing here in town. I'm also a vice chair on Technical Committee 511. And I'm going to talk a little bit about what that means and what Technical Committee is and how you can get involved. First of all, before we get started, just with a show of hands, has anyone been to an ASHRAE conference, either a winter conference or a summer conference? So we got about a quarter of the people here. So let's talk about how we can get a few more out to the society sorts of things. Behind me here I've got the mission statement from ASHRAE's website, what ASHRAE as a society actually does. I'm sure you've all read this many times, but the part I've highlighted at the bottom here is the most important bit. And that is that ASHRAE works and interacts with the world at large through research, standards, writing, publishing, and education. And most of that is handled through society as a whole and then disseminated through the chapter structure. Next slide, present. So ASHRAE works on a local basis with chapters as we are here tonight, where we exchange expertise, disseminate the information and the latest standards from society, engage in fundraising activities, and so on and so forth. But on a global basis, at the society level, ASHRAE works behind the scenes developing these standards and guidelines, producing some of the research, and putting the research dollars we raise here to good use, providing education through seminars and the speakers that travel around, as well as working with different organizations that support government advocacy, helping code write, things like that. Now the key here is that ASHRAE, even though it's a larger society, it is almost entirely volunteer-based. And so it depends on the efforts of people that we need to keep it running. What I'm going to talk about tonight is a small portion of ASHRAE society as a whole. I've put up sort of the whole matrix and organization chart here. But we're going to focus on the little area in blue. And this is a subset of the Technology Council. And it's where we focus on the technical activities. And that is generating the standards and disseminating that information, conducting research. And I'll talk about how some of that comes to be. ASHRAE has 4 different types of committees that focus on the technical aspects of HVAC. The first and most common is what's called a technical committee, and that is something that I'm a member of. My committee is Technical Committee 511, and we focus specifically on humidity control. There's also task groups that get formed when special tasks come up or when society recognizes a high priority item. There's a technical resource group, which provides knowledge in a specific area and supports other aspects of society. And then a multidisciplinary task group, when they realize that a certain task or a certain project is too big for any one area of specialty to work on. And things like energy efficiency fall into those categories. So who actually ends up being on these committees? And it's entirely all volunteers. ASHRAE goes through great lengths to make sure that the committees are made up of a variety of different stakeholders within the industry,
And whenever we have a committee or have a committee meeting, we have to have balance on our committee. And that means that we need to have representatives from the engineering community, manufacturing, research, universities, utilities, regulators, contractors, pretty much anybody that has a stake in the building industry can be part of these committees, or anyone at the public at large, in fact. Typical committee is 6 to 18 people, which you can have a minimum of 6 voting, maximum 18. But there's other types of memberships and other ways to participate in these committees, even if you're not in the core group of people that vote on issues. And that's through being either a corresponding member, which is actually even a remote position. You don't need to show up all that often. But that means that you're kept in the loop and that you're aware of what's going on within this certain community. And there's a provisional corresponding member, which I'll show you a little bit later on here. Technical committee is structured as a small committee. There's a chair, vice chair, which is my current position this year, a secretary, and then several different officers that take care of roles and responsibilities on the disseminating information. And that includes our webmaster, liaisons who interact with some of the other committees on our behalf, as well as the members that actually do the work. Every technical committee is also assigned a few different areas of expertise that we have to look after. Handbook is a big one, so we're assigned a chapter of the handbook that we have to keep up to date with the latest and greatest information. Research, this is how the research dollars actually get spent. Members on the technical committee sit down and debate what's of value and where we have gaps in our knowledge, and then we put together proposals to spend some of the research money that gets brought in from the local chapters. Programs, if you've ever been to an ASHRAE conference, there's a whole technical and seminar and program that goes alongside of those, which is a great way to learn about different aspects of the industry and what's new. The technical committees are typically ones that put that information forth. We structure or come up with an idea, present speakers, and often even speak at them ourselves. Standards, typically certain standards fall under the responsibility or closely affiliated with the technical committee. And then other work as well, things like videos, promotional material, all that kind of stuff. As I mentioned, technical committees are divided into areas of expertise, which are called sections. My committee, 511, falls under section 5, which is ventilation and air distribution. And you can see that we cover pretty much the entire built environment through the different areas of expertise. So some of the things we do. Research is certainly a big area. The research project 1630, that's one we just completed within Technical Committee 511 2 years ago. We realized that there was a lot of gaps in the ASHRAE standards when it came to specifying what amount of humidity should be in a building. And there's been a lot of research done this dating back from the 1940s and onwards. And some really fascinating studies that have come out in the last couple of years related to how humidity actually affects your body's ability to fight infection and its ability to remain healthy. And so this project was a starting project to gather and collect all of this information into one location. And we were able to publish a report. The last conference we actually did a seminar on this. We'll have a few others coming up at upcoming seminars. Standards is also another major task that we undertake. There's several standards that are typically associated with a given committee. It's their responsibility to keep them up to date and find people to work on. Again, it's all volunteer work. And so if you ever found something in a standard that you thought is inconsistent or you could help or that you can make better, by all means, please come up to some and try to join up with some of these committees. We're always looking for volunteers and people that are willing to do the work. The handbook is another area that the technical committee is responsible for. My committee 511 is responsible for the systems and equipment, chapter 22. They're revised every 4 years, so in the time in between, we're constantly gathering the latest in research, writing new sections, updating graphics, and working on improving the package as a whole. We usually form a smaller subcommittee to get together on that, and we're actually just then finally, programs is a major area that we focus on as well. This is actually disseminating the information through conferences or through traveling around to the different local chapters and providing speakers to actually get out there and get this information out. Photo we have in the bottom corner was actually from the last conference here in Chicago. We put together a 90-minute seminar on humidity and health with 3 or 4 speakers. Quite well attended actually. Typically you'll get about 100 to 200 people out to some of these seminars, so it's a great way to get a lot of information. Technical committee meeting would typically look something like this. This is a little bit of a bigger committee, Technical Committee 1.4, which focuses on controls. But what you have is the main table with your core group of voting members, and then you have on the sides, in this case, a variety of other people that are either interested in finding what's going on or contribute different ideas or support the main committee in doing their work. Our committee 511 is not quite as big as this. We typically get about 30 people out for our meetings as opposed to maybe the 100 that you see there. Technical committees meet in person twice per year, and they're pretty much always at the conferences. If a committee is very busy and they have lots of work on the go, they'll often meet more often through conference calls and sometimes rarely through in-person meetings. If you've never been or you've never had an opportunity to check it out, definitely coming to the conferences is a great way to start. We just went through the 2018 conference back in January. Upcoming conference this summer is in Houston, Texas. And the 2019 conference is actually going back to ASHRAE's headquarter town in Atlanta. That's the first time they've been there for a while. So if you're looking for a great way to meet the Winter Blues, Atlanta would be a good choice. A little bit more about my committee. I've already touched on a few of these items. We're responsible for several different standards. Standards in the 164 series. These are method of tests that the industry uses to come up with a level rating system for their products. You'll find this from not just humidifiers, but chillers, air numbers, fans. It's the technical committees that are setting how these things are actually tested, so that when you get a spec sheet, you can be sure that it's all consistent. Research we talked a bit about, programs we talked about, so how do you get involved? ASHRAE's made it easier than ever now. You can simply apply right on the ASHRAE.org website. All you have to do is sign on to the website, click on technical resources, and then click on technical committees. They provide a great list of all of the different committees that are out there, so you can find one that's of interest to you or is aligned with your area of practice. And then simply click on the button to apply for membership on a technical committee. That automatically gets you in the loop. You become a provisional corresponding member. You get copied of all of the information, the discussions, and you're right away part of it. To move up from a provisional corresponding member and actually get into the main committee, you either have to contribute something or show up at one of the meetings and you're pretty much on. And it's pretty easy. Most committees are almost always looking for more people, so please don't hesitate. One other thing I'll just point out, there's often been a misconception. To attend a conference and go to the seminars, there's a registration fee associated with that. If you're going simply to attend a technical committee meeting, there's no charge associated with showing up. It is free to be part of a technical committee. If you've never had a chance to get started with society, I really encourage you to. Certainly I'd recommend trying a winter conference. They're held in conjunction with the AHR Expo, so you get twice as much value for your money. If you're thinking about Atlanta, ASHRAE.org/Atlanta has a lot of great resources to help plan the trip. They can group hotel rates. There's all kinds of things you can take advantage of to show up. Seminars are a great opportunity to learn new things, as well for all of our professional engineers in here with the new PEO program. Attending seminars count towards hours for that. You can pretty much cover 10 to 12 hours of peak hours simply by going to one of these conferences. It's a great way to keep up your continuing education requirements. While you're there, drop by a TC meeting, get a feel for what it's like, make some new connections, check out some of the ASHRAE networking events, or be sure to visit the trade show as well. I think that's pretty much all I have. If there's any questions, I'll entertain them now. If not, thank you for your attention.
Thank you, Nick. And yeah, if there's any questions about wanting to join committees or anything, you can approach anyone from the BOG or volunteering at the chapel level as well. So we'll maybe take 30 seconds here or a minute while we're getting set up for the presentation, and then we'll introduce the speaker. So yeah, why don't we do the raffle now? Any last minute raffle purchasers? All right.
So in just a second, we'll maybe get Manuel to draw the winning ticket. Sure. But we have raised $560 towards ASHRAE Research Promotion. And the winning number is blue ticket. 9, 8, 6, 8, 7, 7, 7. And it's Evans. Big round for Evans.
Okay, I do have my mouse. Yeah, okay. Let's try that for now.
Okay, everybody. And we'll set you up.
Okay, so if everyone's got settled, got dessert, got coffeeed up, we'll introduce our program speaker for the evening. So today we've got a program on acoustics supporting sound mechanical HVAC design. So occupant comfort, limited space and energy available, initial and operating costs. There are many challenges encountered in today's building designs. Mechanical HVAC system designers should consider some of these key noise-related factors and the available tools to avoid potential issues on the projects. Presentation entitled Acoustics Supporting Sound Mechanical HVAC Design will discuss cost-effective design strategies and a range of evaluation methods to help achieve acoustic success. So our speaker is Emmanuel Moratitas, Master's in Engineering and a PhD, Director of Acoustic Engineering at VAW. Emmanuel is the Director of Acoustic Engineering, noise control manufacturer based in Winnipeg. In his role at VAW, he manages the firm's noise control laboratory, special applications engineering, and software development. He's a professional engineer with a Master's of Engineering in Acoustics from Penn State, and active at the ASHRAE and ASTM committees for acoustics. This includes work as a lead investigator in the ASHRAE research project on the aeroacoustic properties of HVAC planners, which received the ASHRAE Symposium Paper Award. Mr. Moratitas has presented research papers at the Canadian Acoustical Association, NoiseCon, and Internoise conferences. Emmanuel has been employed in noise control manufacturing, applied research, and acoustic consulting field for over 23 years. So without further ado, I'll introduce you to the speaker for the evening, Mr. Emmanuel Moratitas.
Nice to be back in Ottawa. My colleague Katie Reynolds and I are going to be standing at the booth afterwards, and if anyone has any questions, comments about VAW, we'll be happy to talk to you there. This is a fairly, I suppose I can describe it as a technical talk, drilling down to various topics in acoustics and applied noise control. By no means am I covering all areas that may be potentially a concern or of interest to you. So if there's any topic that I either completely miss altogether or don't provide sufficient detail, please let me know and we can talk about it afterwards, or my card is on the table and I'd be happy to talk to you afterwards. Perhaps myself or one of my colleagues can help you further. So, it's a shame I can't stand this one. The noise, acoustics in general, it can be a common complaint with regards to indoor and outdoor environments. It's a key component of whole building comfort. One of the key components, nonetheless. If ignored, it may result in occupant complaints, costly repairs, project delays, and a very interesting situation when it does occur, loss of use of space, if you will. And the best example, or one of the common examples you will encounter in this situation, you'll have a large multi-use space in a building, perhaps a cafeteria that also has to act as a music space and a performing space, for example. If you miss some key components as far as acoustical design are concerned, that facility, that building owner, that school perhaps may lose one of those functions as a result of noise. And when it really goes bad, I suppose it can even damage the reputation of the team that's involved. So the focus of this talk is to review practical, cost-effective techniques, highlighting various areas that both obviously myself and probably some areas that you encounter as well. The motivation is to help provide you with information that can help you achieve, if you will, more likely to achieve acoustic success on each and every one of your projects. And recognizing that acoustics sometimes plays a limited role in some facilities and some aspects, but sometimes plays a very prominent role as well. So I'll provide a brief introduction. A brief introduction on VAW and my role at VAW, give you a little bit more background information. Then the two main components of this talk will be what we'll call high-level strategies with regards to applied acoustics, and then we'll drill down, as advertised, into some very specific details, design details. And there's one, I'd like to get, there's probably several case studies, I believe, on this slideshow, but I'd definitely like to get to one case study at the end, and we'll round up at that time. VAW can be described in, if you will, four parts, four areas of focus: commercial HVAC noise control, industrial fan silencing systems, gas turbine power plant type noise control, dealing with not only noise control, also air filtration and ducting systems. And another area that's kind of a hybrid or industrial and power plant work is what we call field services, retrofit services, where we go into existing power plants, as an example. They may have 25, 30-year-old equipment that's rusting out, breaking down, as it tends to in a power plant that runs nearly 24/7. And with that, you simply go in and swap out and improve the existing noise control systems and ducting systems. So that leverages our expertise in industrial and power plant noise controls. My particular area of focus, as noted earlier, is acoustic engineering, applications engineering, software development, and R&D. I'm based out of Newmarket, just down the road from you folks, where we run our air acoustic laboratory. Katie Reynolds is out of our head office and main plant in Winnipeg. In the lab, our primary focus is not only characterizing, if you will, the black box of our products, the silencer quite often, but also how that black box behaves in a real system situation. So we call them system effect evaluations, system analyses, where we're looking for the air acoustic properties of that particular product behaving in a real life system. We consider that as important as rating the black box itself. But we also do a lot of independent lab testing as well, and field verification studies, goes without saying. Now, commercial noise control can be come in various shapes and sizes, and as I mentioned earlier, various intensities of complexities and cost, quite frankly. But I guess the top of the food chain in noise control in buildings can be described in three main areas: performing art spaces, very low background noise levels, and room acoustics is very, very important. Various healthcare facility applications, and the general group of what we call high-performance buildings. And the high-performance building, the energy-efficient office building, a pharmaceutical operation, there's many varieties of that. What actually makes it a challenge from a noise control perspective is not necessarily the acoustics. That goes without saying. You can have noisy pieces of equipment that need to be addressed. That's true in every facility. But the drive for energy efficiency in that high-performance building and the architectural treatments that we encounter whenever we walk into a modern atrium, shall we say, there's very few sound-absorbing surfaces to work with. So that presents a challenge for the whole team. How do we get the background noise down to acceptable levels while knowing the fact that we're basically in a gymnasium that we're calling an atrium? It's a challenge. So you'll see when we talk about strategies how we try to avert problems and come up with cost-effective solutions. Here, I suppose in all our practices, every project tells a story, shall we say. So here's three really brief, rather recent stories that we've worked on that you may be familiar with the facility, so they're chosen for that reason. On the far left is the Apple headquarters in California. The background story there, the thing that piqued my interest was there was extensive cafeterias in that building. I was quite shocked as that when I heard how many ventilation systems were just associated with kitchen exhaust in a massive facility such as this. Each one of those silencers had to be packless, what we call reactive silencers. So there's no media fill whatsoever in them. That's fine, that's very standard, but they also had to be cleanable to meet some NFPA standard that you folks may be familiar with for any kind of grease buildup and that sort of thing. So indirectly, it made the noise control quite a challenge because a packless silencer is analogous to your car muffler. There's various chambers behind the perforated metal inside the duct. And the placement of these access doors for the cleaning resulted in quite a challenge in terms of getting the chambers to work just as we wanted them to work for the various fan systems. So it was, and no, there was no two silencers alike, shall we say. They were all unique as far as their design and installation. In the center, it's probably crunched up where you're sitting, but that image is the Comcast building in Philadelphia, a textbook example of extreme system effects. High duct velocities selected for various reasons, and many duct components sitting on top of each other. An elbow followed by a transition, followed by an elbow, and you know the drill, with no space whatsoever available between the various components. So again, that was an aerodynamic challenge, a very interesting walkthrough. The far right is a really good example of a retrofit application. That's the Arthur Ashe Stadium in Queens, I believe. And there they ripped out the entire mechanical system and upgraded it. And by upgraded, they wanted better acoustics and, I guess, more air. So the air handlers were larger. The structure did not change, as it normally does in these situations. The air handlers actually sit immediately behind the seating areas, as they do, I think, in most sports stadiums. And as I said, the air handlers grew by a certain percentage amount, so that left even less space for the silencing. And by the way, we needed to deliver more silencing, so it was a neat little application of compact noise controls. A little bit of hometown pride, if you will. That's some projects we worked on right in Winnipeg would be the Museum of Human Rights. That's in the right downtown area. If you happen to be visiting Winnipeg, and perhaps if you visit Winnipeg recently, I definitely encourage you next time you go back if you happen to visit that museum. The upper right-hand corner is the relatively new Winnipeg Airport. And last but not least, when the Jets came back to town, there was a renovation again of the mechanical system at the MTS Center. And we were quite proud to be working on that one as well. Okay, so there's going to be a particular focus on noise control, but we will talk about a few general topics on applied acoustics as well. So a lot of things that we're going to talk about right now kind of set the table for the detailed design section that I talked about earlier. This is as well. I'm actually going to skip this intentionally because there's another slide that actually covers this. Just a few more samplings of the type of noise controls we encounter. The far left is what we call a fume hood silencer. It'll be a packless silencer that possibly goes into a lab ventilation system. At a university, for example, it's very common to have an array of fume hoods that each need to tap into their unique stack and silencing. The other pictures are sort of self-explanatory, but the rather dull-looking image, unfortunately, is a fairly important description of what we call an extended width silencer. It's actually made out of 10-gauge molded steel as well. That was done for acoustics. But it may not be clear from your vantage point, but that has a particular duct connection size. we'll call it 24 inches wide. And the casing extends out another 6 or so inches out away from that silencer. And that is a very typical solution for your high velocity systems. So if you happen to have to push the velocity, let's say above 1,500 feet per minute, maybe even above 2,000 feet per minute, you're ducting, which is getting a little critical, of course. One of the effective ways to deal with those high internal velocities is to go with an extended width design. But I have a graph a little later that shows the benefits of that as well. Other products, quickly, that we also encounter in our HVAC design are acoustic enclosures that are fabricated from acoustic panels. Some decisions, a vital decision that you need to make whenever you're talking about an enclosure or a panel system would be the supporting equipment that's related to acoustics. So an enclosure needs to be ventilated, so how do you ventilate the enclosure without compromising the acoustics? Perhaps you add an acoustic louver or some sort of elbow silencer or some sort of silencing system. The doors, you need to be very careful what types of doors you specify, windows, etc. And then the decision on where does that enclosure sit. Does it sit on a pad or is there a separate structure required, and how do you deal with the structure? Acoustic louvers are, I like to nickname the noise control last line of defense. When you literally have no more space in your system, a typical application or situation may be a genset, where you literally only have the block wall available to you, 12 inches, 16 inches of depth, and that's it. You can, in lieu of a rain louver, you may choose to go with an acoustic louver. Far left is a standard blade louver. In the center, well, we call it a site-proof louver. So it has the added acoustic benefit because it's bending the air and the noise 90 degrees as opposed to the standard blade louver. There is that improvement, but they're very effective at providing security in terms of no line of sight into the building from the outside. So that's typically why we would choose those. On the far right is an airfoil shaped louver. By far the lowest pressure drop solution in all of this, but it comes with a little bit of a penalty in terms of acoustics. They're not quite as high performing as the other two. And another aspect of this is, in particular, if it's a retrofit in an existing system, you need to maybe boost another 8 to 10 dB insertion loss, or for what it's worth. You may take an existing rain louver and add some baffling immediately behind that rain louver. That's a very cost-effective, again, and a low-pressure drop option, where you have specially shaped baffles that go right behind the louver. Okay. Now the strategies, that high-level information. There's about 5 or 6 slides that deal with these strategies for success. At the very beginning, try to get buy-in from everybody, starting from the owner or the owner's representative on down through the design team. The buy-in that acoustics is going to be a big part of the decision-making process going forward. As early as possible, at the 80% design stage, get it in as early as possible. And clearly define what your acceptable noise levels are, and possibly even red flag the critical areas of your building. A critical area is twofold. It's the critical spaces, space usage. So in a university, it'll be a few key lecture halls, perhaps, some laboratories. So perhaps we red flag those spaces with red, and we choose another color and we red flag, or we flag out the areas with the noisy equipment. And you can quickly get a spatial appreciation of where is your noise coming from and where do you want to avoid it going. And get an idea and kind of get a lay of the land. I'm describing what's actually kind of a complex process, but a vital one nevertheless. And I like to describe it as the formation of a noise control team. Architectural lead in the project, a mechanical design lead, an acoustic consultant, which is, depending on the complexity of the project, is likely going to have an acoustic consultant involved. Leaning on your noise control suppliers is another effective member of this noise control team, and any kind of specialist stakeholders that may be required, electrical and structural guys. Sometimes some key noise control decisions trigger the review of others on the team. So identifying the key people right at the onset is probably an effective way to work more efficiently and to achieve success going forward. Then another, you may have heard this some term when it comes to noise control. Manage your footprint, your mechanical footprint. And that is try to locate noisy equipment as far away from the receivers as possible. Easier said than done, but the quietest air handling unit is the one that's 500 feet away from your room. But in the real world, we can't achieve those distances, but we can perhaps maximize them, improve the mechanical footprint. So here are just a couple of discussion points, indoors and outdoors. We'll ask ourselves, how much natural attenuation am I getting out of my system? It's a term that's probably not used a lot these days. I'm kind of dating myself, but when I first got into the industry, there was always this informal discussion and review of natural attenuation. It really was all about real estate, how far away you can get things in your system. So let's take an arbitrary sheet metal duct size and just evaluate in the low frequency range. And you'll see, for reasons, graphically you'll see in a moment how important low frequency is to your overall design decision-making process. But take my word for it, but in the low frequency range with, let's say, 63 hertz, if you only had 10 feet of bare duct available, you can anticipate an attenuation level of, let's say, 10 dB. But if you can somehow stretch that out to 40, seems like a big jump, you'll gain another 8 dB, if you will, free noise attenuation. And of course, everything comes with a price. You're paying a penalty of space allowed, but perhaps if you can cleverly design that into the system, if you will, it is free acoustics, free noise reduction. Another technique or another evaluation that you can do in the great outdoors is you can ask yourself the question, am I maximizing my divergence and barrier losses? Divergence deals with how sound decays over distance. We call that divergence, but some people call it a distance loss. So the greater the distance, the greater the noise reduction. A barrier is self-explanatory. Here's a few talking points. If you're only 6 feet away from a point source, like a centrifugal fan sitting on a building, or the termination of a stack on the top of the building, or that grade, you'll get about a 16 dB reduction. But if you can move that equipment another 6 feet away and double the distance, it'll increase to 22 dB. So it goes without saying, the greater the distance outdoors, by virtue of the fact of the divergence losses, the acoustical spreading over distance, you'll gain a great deal of attenuation from the system. Now, so we talked about maybe laying out the mechanical plans all over the architectural plans at the early stage. Another thing that we can do, it goes without saying, is lay out the mechanical rooftop equipment at the early stage and look at the relative location of noise receptors around your building. Perhaps there's only a residential development on one side of your facility. So by virtue of distance losses, I'm going to try to maximize the separation distance between that property line and all of my noisy rooftop equipment. The little stuff we can ignore, we can be practical. But the large cooling tower, the really large air handlers, gensets, we try as practical as possible. We try to move them as far away from the receptors as much as we can. Now, barriers, they come in all different shapes and sizes. A barrier could be literally a noise wall, it could be a berm, it could be a building, it could be buildings, many buildings between your noisy equipment. We try to take advantage of that. We try to, as much as possible, put things behind either natural or man-made barriers. I'll jump over that. Here's a real-life example, or a situation where it never went down this route, but it's a good story to tell in terms of not taking advantage of advantageous barrier losses. Here's a pharmaceutical facility on the right. On the far left is a residential development and green space in between, but not very much distance, a few hundred feet. And like a lot of pharmaceutical companies, a lot of pharmaceutical manufacturers, they've been growing a great deal over the last few decades. And the facility started off as a relatively modest operation, almost off the map, south. And they continued to grow north, adding more and more labs and processes, et cetera, et cetera. And the straw that killed the cows back was at the far end, they put two large FRP fans on the roof of their building, and that drove the neighbors bonkers in terms of noise. They were putting up with it, they were putting up with it for quite a while, but apparently those large FRP exhausts were just too much to take. There could be a psychoacoustics evaluation here too that could have been made, that the building became barely noticeable to this big behemoth. So there is a correlation in the literature that you'll find between people that see something and their ability to hear it. Quite often, if it's really ugly, if you will, and noticeable, they'll tend to complain about the noise, more so than if it was completely shielded from it. So unfortunately, there wasn't a big forest between the plant. Nevertheless, we're drilling down. When you zoom into that area, the new-ish part of the building, I guess it was the newest part of the building, you have your FRP fans at one end, at the west end, and the east end. And while at the facility, I asked the facility manager, what have been, I noticed that the buildings on the left and the far right-hand side, they're about 3 stories high. And then the building kind of dropped down one level at a time, down to almost gray, at grade in the center that are pointed out by the red arrows. And I asked a simple, curious question. Could you have moved those fans in that pit? I call it a pit. And he pointed out, yeah, we didn't think of it. It may have been a little bit more costly to rub the piping there, but we could have done it. And it would have, so with this particular application, they had a noise problem with regards to the casing breakout noise of the fan. FRP fans are kind of susceptible to that, and the exhaust noise. It turned out that if they had, the ship had sailed, of course, since they were not going to move the fans at this point, but they needed significant noise barriers in addition to the discharge silencer. If they merely had dropped the fans in that pit, the casing noise would have been a non-issue. They only would have required discharge silencers on the roof. So a big cost penalty from not just not going through a planning exercise. Selecting suitable construction materials is sort of self-explanatory. If your spec is going to change from stainless steel to aluminum, kind of a big deal with acoustics because of the difference in mass is going to potentially impact how much noise is radiating from your ductwork and potentially your panels and your silencing, etc. So being aware of that, that's sort of self-explanatory. But observing the speed limits, what I mean by that is this is kind of quasi-objective evidence. Depending on what source you look up, you get different opinions on this. But it goes without saying, though, that if you can kind of limit the velocities inside your duct, you're going to avoid problems. There's a really good book by Mark Schaefer, which is an ASHRAE publication. It's about 20 years old, 15 to 20 years old. So, yes, it's a little dated, if you will, but it's an excellent resource for things like this. And in that, there's a couple, maybe 3 pages devoted to describing velocity limits, recommended velocity limits for various fittings, and in this case, just quantifying various velocities of main ducts and branch ducts relative to a desired NC. But you'll notice in that chapter as well, there's no actual calculation. It doesn't imply that every single room that you're shooting for NC35 will be fine if you limit it to 1,000 feet per minute. But it'll get you close and it'll keep you out of trouble. A calculation at the end of the day is warranted each and every time, but this is really, really good information, or really good rules to follow, shall we say, especially when you're initially laying in your system. And now, diffusers, grills, and dampers. They have their own concerns when it comes to acoustics with regards to how much noise they're going to generate. Here's an example of a manufacturer's data sheet that's very common. This happens to be an air grill, it's a supply diffuser. But I believe it comes to the fact that they have to follow the ASHRAE standards for reporting their data. A lot of the summary tables in the manufacturer's data sheets kind of look like this. So this is what I'm describing here is very typical for manufacturer to manufacturer. It's industry driven. They provide various aerodynamic information, geometric data, and acoustical data on the far right. A couple things to point out. They rate their diffusers against an NC, noise criteria, room noise criteria. But everything has to be baseline, of course. So according to the standard, the NC ratings for any air diffuser is based on an acoustically soft room. What's an acoustically soft room? I'm going to use this term again later, so I'll describe it now. In the industry, that's typically a carpet floor, gypsum wall, acoustic ceiling tile above. That generally describes an acoustically soft room. That's some debate there, but that's generally what we would call it. So if you have something other than that, you have to be careful. If you have a pool, a gymnasium, a large meeting room like this, you may not have an appropriately rated acoustically soft room. So something to be aware of when you're looking at manufacturer's data. No 60 Hz data that the standard is producing for very low frequency values. And that could be a problem in certain applications. And finally, the sound levels themselves are based on ideal conditions going into your diffuser. Makes sense. You have to baseline things. I come from the silencer world, and we have a test standard that baselines the black box, ideal in, ideal out. Same thing with the diffuser world. But let's dive into my son's hockey play. I thought this was a good space to take pictures of some real-life air diffusers without an exposed ceiling. In the real world, supply and return air grills rarely have ideal conditions coming in and out of the unit. And here's another example that appears to have seen the wrong end of a hockey stick. Okay. So these things, we have to be practical. We have to be aware of how the product's being applied in the real world in your system. So with that, one of the techniques that we try to apply, within reason, we try to maintain space. Right? In a perfect world, you have 3 to 5 duct diameters away from every component. And that, I don't know if that building has ever been built, but that's your idealized case. So there's no airflow, adverse acoustical interaction from component to component to component. The APCA standards and ASHRAE guidelines, for that matter, are an excellent resource there, and folks may regularly reference these things. We'll talk about, I believe I have a couple of slides on fan system effects. And specifying quality equipment. Well, I think whether we're buying a refrigerator or we're buying a fan, we can assume that perhaps the more we spend, the better quality we're going to get. And in the acoustics world, a sound rating is a sound rating, of course. If it's based on a lab test, it is what it is. But the other side of the coin is if it's a poorly built component, perhaps the way it's fabricated, the materials it's used, etc., when that component ends up in your system and it's under real-world stresses and pressures, shall we say, you may get something completely different. So, but I believe there's a big gaping hole in our industry with regards to correlating equipment cost and sound quality. And the sound quality metrics I'll mention in a moment, but I might as well mention them now, it's a good time. By sound quality, I don't just mean the actual emission of sound, the sound level. I mean, does it create a lot of rumble, low frequency noise? Is it tonal? Does it vary unnecessarily? Is it what's called quasi-steady noise as a result of real-life installations? That would be an excellent research paper, I suppose, or several research papers that someone may do one day. And avoid undesirable operating points, surging fans, nobody's friend. So there's a lot of things that we consider or have to evaluate from a project-to-project basis, some more than others. And when it gets really technical, shall I say, it's probably a good time to call in an acoustics expert. You folks are fortunate. In your market, you have several acoustic engineers. Some markets I visit, the US in particular, smaller cities, have no acoustic engineers working in their background, in their backyard, pardon me. So it's actually difficult to retain one for a project basis. But nevertheless, in my opinion, some of the trigger points are high-performance buildings, mixed-use spaces, extremely low noise criteria, the classic lecture hall, theater space, unusual noise paths. If you have a mechanical room and you have a room next door, that's not really unusual, that's pretty typical. But sometimes noise tends to take a fairly interesting and non-linear path through your mechanical system. And sometimes it's of value to have an acoustics expert to look at it. And finally, if there's a potential for a mock-up test, perhaps you're using a new technology or a new approach, or it's just really required because of the sensitivity of the project. Mock-up testing can be performed in the lab, in the factory, as you know, or at the site. But that's a really good time to consider bringing in an acoustic engineer that can kind of quarterback the whole thing. Okay, so final area is the meatier area of this as far as technical stuff goes. And I want to apologize ahead of time. There's probably going to be a few graphs that you're not going to be able to read, especially folks in the second row. I apologize. The X and Y axis is going to be a little bit difficult. I wasn't planning for such a large one. So we'll talk about the application of noise criteria and what it may mean to your system specifications and designs. We'll cover noise path analysis with a particular focus on not actually performing a noise path analysis. You may not care whatsoever about that, but it's some of the key decision-making processes that may occur throughout your project. And if you're not aware of how they impact the noise path, you may not be taking advantage of things that are actually available to you. In other words, flipping from one type of component to another type of component may have a big impact on acoustics, and you may not be aware of it. So by highlighting the various key elements of the noise path, perhaps there'll be some interesting points that you may consider for your next HVAC design. And then we'll get into the philosophy part of the presentation. We're talking about controlling the noise at the source. But we'll talk a little bit about silencer characteristics and aerodynamic system effects. So NC levels are kind of the go-to criteria in our industry, but there's quite an alphabet soup of lexicons and acronyms for noise criteria. Probably the next most common is the RC method, but NC is sort of a time-tested criteria for indoor noise, where we have a single number rating for a given space. And the ASHRAE chapter is an excellent resource for this. The NC curves themselves, the history behind them, I'm skipping a lot of detail now, but in brief, the history behind them is through some psychoacoustic testing that they did in the 70s, where they did jury trials and subjected the jurors to various sound level intensities across various frequencies. They came up with equal loudness curves. And in general, what it means for you to perceive a particular sound level, let's say at 2,000 hertz, you would need a lot more energy, sound energy in the lower frequencies, so that you would perceive it as equally loud, I guess we can call it. So there's more credit to get into the lower frequencies, and that really just deals with the way we process sounds. So that they leveraged that work, and out came the NC curves. They're sort of the reciprocal of that research. But not the problem, but the thing to watch out for NC is, I like to say, not all NC is created equal. Here we have 3 different profiles. Each one of these is a valid NC 30 criteria. It meets NC 30. The solid red line is what I would call a well-behaved room, where it, shall we say, hugs the NC 30 profile fairly closely. So that's the literature suggests that that's a rather desirable spectrum. If anything, you'd want maybe a little lower sound energy in the lower frequencies, but it's pretty good. If you designed a space and went in afterwards and measured it, and you got that solid red line, you'd call it a pretty good day. Now, if you had the second line down, that's not such a good day. The small dashed line, for the folks that can't read it, that's the one with the peak at 250 hertz. That's a really bad situation, potentially, because that implies that the system, for various reasons, may have been over-attenuated, and it's revealed a peak, likely a peak frequency coming from a centrifugal fan. You're very likely, or at least likely, I hate using qualitative language like that, but you're likely going to get noise complaints from the receptors in that, the workers or occupants of that space. But then you could say, well, goodness, I'm doing really well at all the other frequencies. Yes, that's actually hurting you in this particular case, because that 250 hertz prominent sound is very, very noticeable to the average listener. So you want to avoid the second curve as much as possible. The third one may not look like a good one either, right? Because it has a funny shape. It's very low in the low end, and it kind of comes up and kind of hits the NC30 curve in about 3 octave bands. But that's a spectrum shape that's highly desirable in open plan offices, call centers. where you're actually looking for speech privacy as one of the major goals. So the HVAC noise is going to provide a little bit of a, not quite white noise, but a hissing sound that's going to do a fairly good job of masking conversation from cubicle to cubicle, workspace to workspace. So it's not the greatest sound spectrum, but it may work for certain applications. Okay. In the outdoors, we're lucky to be working in Ontario, and perhaps you guys do some projects in Quebec as well. Those two provinces are well known in Canada as having fairly well-defined outdoor noise criteria. I work in basically every jurisdiction in the US on some level, either directly or indirectly in projects. And it is amazing how it differs from state to state. We go from some states that mirror Ontario almost exactly. Here's the standard, here's the regulation, etc. So everyone understands the yardstick that we're going to be measured against. To the other extreme is we don't have any criteria. We used X ED in the last project that seemed to be okay. Go with X. Without any, that has very little technical standing. Whereas the MOE guidelines, for example, for outdoor noise, if you drill down through those guidelines, they reference papers and studies, etc., that sort of support where they're coming from. And it's consensus building guidelines, of course. There's acoustical experts that are working on those guidelines regularly to come up with better tools. And a little nuance about outdoor noise as compared to indoor noise. Indoor noise going from the equipment to the receiver is self-explanatory. Outdoor, it may be the property line. It's always the property line. But it can also be what we call sometimes self-contamination. It's a window, a patient window for a hospital, a classroom window for a school application. That actually becomes the big deciding factor in terms of what you're doing with your mechanical system. Okay. Now a little bit more on criteria. Those are the basics: indoor, outdoor. If for higher performing buildings, or buildings with perhaps there's 15 regular off-the-shelf, if there's such a thing, air handlers on the roof, but then you have one particular fan, high-pressure blower, maybe a baghouse system, if the building requires it, a large cooling tower that could be one or two trigger points in your job that you would be really concerned about with regards to noise emissions. You may want to consider adding a tonality criteria to your specification. And you put the burden on the equipment manufacturer, and what you say is that they need to do a third octave band evaluation. And we haven't really talked about octave bands and overall levels. In the interest of time, I kind of skipped that. But a third octave band evaluation is a little more challenging. You're putting the burden on the manufacturer to have that data or the ability to come up with that data for their equipment. And this standard, ISO 1996, is one of my favorites because of its simplicity. It merely requires that any given third octave band level cannot exceed the adjacent third octave band by a certain criteria. Either you have it or you don't. What the standard says is that if you exceed these levels, 15, 8, and 5, in those frequency ranges, you are likely to have complaints due to tonality. In other words, you have a tone. A tone has appeared. So that's one very simple, straightforward way to specify tone criteria. Now, low frequency noise. Low frequency in the HVAC world is basically any sounds 125 hertz and lower, down to 32 hertz, let's say. That's the low frequency domain. Quite often, luckily in the HVAC world, a lot of equipment does not generate sufficient sound power in low frequency range to cause a problem. A lot. But some that do can create huge problems, huge cost potential problems with regards to mitigating it if you happen to have it after the fact. So how do you avoid it? Well, again, we didn't have time to get into the arithmetic, but I can leave you to look these details up. There's an ANSI standard. There's an ANSI standard, 12.9, that talks about the evaluation of TBC versus dBA. Again, not going into the details, but you're looking at the delta between those two overall values. If it exceeds 10, you may have a problem for low frequency noise. If the delta exceeds 20, you most definitely have a problem, because that's a very significant threshold to be over. Another way to evaluate low frequency noise or potential low frequency noise is to look at the explicit sound pressure level in a space. And that standard also says that for any indoor space, you should never exceed 70 dB pressure. And that corresponds to NC 50 for what it's worth. So even for your less critical spaces, you do not want to exceed 70 dB. And quite frankly, you should shoot for a lot less than that. Okay. A little bit on path analysis. So when we talk about a noise path, we can break it down into source, path, receiver elements. If we had this lovely dinner 20 years ago, I'd probably spend half of this presentation talking about the needs and the issues associated with getting good equipment ratings, sound ratings. But starting with the fans with AMCA in the 90s and moving forward to virtually every piece of equipment, I'm sure you folks can readily get octave band sound power ratings for virtually everything you're applying in a building, whether it's the gen set or the pump and the cooling tower, et cetera, et cetera. So that's almost off the table in terms of being a going concern. On the receiver side, it's hard criteria or noise guidelines, if it's the MOE. Those are the tools that we go to. There's also a little, and space usage, there's also customer expectation. Having some soft skills in this area in terms of understanding what the customer desires. And one scenario that I've encountered in the past is you receive comments such as, there's a building owner that builds a similar building once every couple of years, and he or she doesn't know anything about the NC criteria for ASHRAE, doesn't care to know about these things. It's not really their concern. But what they do know is that however that last atrium that they built worked wasn't to their satisfaction. There was something about it that they didn't like as far as HVAC noise. And that's good to know. What was it? And you would ask the follow-up would be, was it low frequency noise? Was it a little too much hiss? There's some characteristics, some trigger words that they may use to kind of set you down the path in terms of getting it right. So that's on the receiver side of things. In the middle, we have the noise path. That's by far the play. If you try to do a path analysis yourself, and like what I like to call the go-it-alone philosophy, where you're not bringing in an acoustic engineer to look at it more carefully, maybe a noise control supplier to look at the duct paths a little more carefully, you may get stuck in the mud there, because there's a lot of details that if you're not doing it every single day, it could bog you down. And here's a kind of a dynamic range of what we're dealing with for each main component. All of these components come out of ASHRAE chapter, but kind of the low end and the high end. So you kind of get a feel for, oh goodness, if I forget something, or maybe if I double counted something, I assumed something was going to provide a certain benefit and I was off by a factor of 2, I could be way off from one end or the other. So it's important to get your accounting right when it comes to the noise path elements. And in my opinion, that's where you're going to spend the majority of your time. And quite frankly, the majority of your technical risk, if you want to call it that, your technical risk as far as acoustics goes, if you break down the noise path elements. Okay, so the next series of slides, I think there's 5 or 6, we're going to talk about each of those noise path elements. And as advertised earlier, we'll talk about some key features of those noise path elements that you may want to consider the next time you're designing your system. In the interest of time, I'll skip the noise rest. I think I said enough about it as far as, at the end of the day, just getting good lab-referenced data, lab test-referenced data from your manufacturer is half the battle, if not more. So now the elements themselves, everything that you see at the top of the screen, the hints and graphics, all of those algorithms are basically out of the ASHRAE chapter and a few related sources. The HVAC plumbing, the current version of the ASHRAE chapter is based on the research that I worked on with ASHRAE in the late 90s, early 2000s. And in addition to obviously specifying the surfaces of your plumbers and the dimensions of the plumbers, those are all going to factor into the performance of your HVAC plumbing, whether the noise source is sitting in the box or the noise is in the air is traveling through the box. It's a plenum, it's still a plenum. One of the artifacts of that research showed that low frequency performance, actually mid to low frequency performance, is directly proportional to the plenum size. The bigger the box, the more effective it's going to be. Perhaps maybe intuitive. but we were able to quantify that for a given volume, as volume varied, the attenuation tract was proportional to that. So the short of it is, the bigger the box, the better. Space allows, of course. Okay, then ducting, the most common thing we're going to have in our system, whether it's round, rectangular, round, or flat oval. Rectangular duct tends to be far superior as far as attenuating the noise than round. But one of the key features of round duct that the other types of profiles of rectangular and flat oval offer is round duct is far superior as far as avoiding breakout noise. So the noise is now traveling through your HVAC system. There's going to be some noise that may escape through the surfaces of the walls. Round duct is far superior as far as dealing with that. An economical way of dealing with breakout noise. As an aside, that's why a lot of theaters tend to have supply ducting that's of round geometry, not rectangular, to deal with the breakout noise. Now, a couple attributes. Well, I think I've said enough. Then we need to specify whether or not the duct is lined or bare. But some of the features are elbows. We have our square elbows with turning vanes and maybe a radius elbow. Aerodynamically, the radius elbow, a nice smooth radius elbow, is by far the superior selection, as you folks can appreciate. Putting several radius elbows in a row in a system introduces almost negligible static pressure loss. But from an acoustics point of view, they're inferior to square elbows with turning vanes. So one thing you may contemplate in your system is if you're, shall we say, a few dB shy, and you from A to B you have several radius elbows in a row. If your fan can tolerate just a little bit more static, perhaps you replace a few radius elbows with some square elbows and turning vanes. I believe from a sheet metal point of view, that elbow is a little more costly, marginal, but it may provide a significant amount, 3 to 6 dB more attenuation than a smooth radius elbow that provides almost no attenuation. So that's one thing to consider. And I always say, don't forget about your 45-degree elbows. They're not to be ignored. They're providing, in the accounting of doing your noise path, they may add a few dB here and a few dB there. Many noise paths that I encounter have several 45-degree bends from A to B. And they add up. They add up linearly to something worthwhile. Branching is another feature. Every time the sound and air encounters a junction of some sort, a two-way or a three-way junction, there's going to be a certain amount of sound that goes in one direction and the other sound energy goes in another. So there's an attenuation associated with that. And then in the miscellaneous category, again, little bits sometimes can be ignored, but sometimes may be of value to you to consider. The attenuation of filters, grills, louvers, and possibly even a damper, a partially open damper, may be advantageous. And in a very critical application, we'll also consider airflow generated noise. Of a silencer, of a damper, of a louver. It really doesn't play a role in high NC applications, NC40, NC45, 85, if you have to achieve an outdoor noise level of 80 or 70 dB, for example, close to the side of the building. It's very rare that airflow noise is going to impact that, just the way sound adds up. But when you're dealing with really low noise critical applications, it's often the driver. If your internal velocities get up anywhere near those threshold values that we looked at briefly earlier, with 1,000 to 1,200 feet per minute, if you get anywhere near there and you have several components in your system, it may add up and be a problem. It may end up being the driving factor of your overall system design, and the only way around it may be to resize your duct. Kind of a costly exercise, but a worthwhile one, because if you miss it, if you miss the airflow noise, it could be a big problem. And last but not least, is the end reflection. So end reflection is an acoustical phenomenon that feel free to, if you're not read up in this area, to go in the ASHRAE chapter. There's a really good section on this. As sound travels through any medium like a duct, or an organ pipe for that matter, and sometimes the end reflection loss is referred to as the organ pipe effect for that reason, it travels down this medium and it hits an abrupt termination. At that termination, a certain amount of sound waves are going to continue on through that abrupt termination, and some of it's going to reflect back. Just by the fact that the sound wave encounters this change in dimension, and it was called acoustic impedance. But this effect is only valid, in literature you'll see this if you go to the ASHRAE chapter, when you have nice uniform duct lengths upstream from the termination. But going back into, so anything that's non-uniform creates uncertainty. Uncertainty in terms of, do I really have end reflection or not? And unfortunately, or fortunately, depending on how you look at it, low frequency is end reflection is a low frequency phenomenon. So it's in that costly area, that critical area of low frequency noise. And going back into the arena, one more time, we rarely have ideal conditions, uniform duct length upstream from a termination. We often have this sort of thing where we have some turns and some transitions and offsets, flex duct. All of these things create an uncertainty to the point where many acoustical engineers, and just my opinion from observation, they'll often ignore end reflection on a critical application. Some will provide a conservative estimate of end reflection loss because they know that when their system is finally commissioned and ready to go, they have hardly any ideal duct runs between the termination and the main duct. Okay. This is what a typical duct path analysis looks like, which is probably completely useless to you from where you're standing. But just to summarize, when we do a path analysis, we'll include a summary of the noise source levels, the different components in the duct system path, the result, the sound pressure level predicted in the room against the noise criteria. The really neat thing about the ASHRAE the ASHRAE algorithms, is its simplicity. All you really need to know when you want to do a prediction of the sound level in a room like this, in a smaller room actually, is the room dimensions and how far away your worst case receiver is relative to the air opening. So in a classroom, it would be the seated location closest to the supply air diffuser, for example. That's all you need to know. But there's a like everything, right? There's a qualifying language in the ASHRAE chapter. I think word for word, it's applicable only to typical acoustically soft rooms. There's that term again. So carpeted floors, gypsum walls, acoustic ceiling tile. If you differ from that, and you have extremely large rooms or extremely small rooms, but I wouldn't worry too much about small rooms, but the larger the room and the harder the room, as far as surfaces goes, the less likely the ASHRAE algorithm can be used. In fact, a more, what's called a higher level room analysis is required that really an acoustic engineer can support you with. And it goes without saying, the pools, the libraries, the atriums, those types of special spaces, large lecture halls, I would stay away from the ASHRAE algorithm in terms of predicting the sound level. Let's just jump through that in the interest of time. Okay, so we're going to get into a few slides on silencer characteristics. Just to set the table, one of the things you may think about is when I'm specifying duct liner or silencer or some sort of noise control measure in my system, is it suitable? And in many jurisdictions, exposed fiberglass is not really allowed, depending on where you're working. But there are some standards that you can reference these components, and the ASHRAE 62.1 standard is, there's probably many experts in the room with regards to that standard. You may recall it references various, some ASTM and UL standards for air erosion and mold growth, and you have to make sure that whatever you specify for your application meets these requirements. But some general concerns, rather obvious concerns for the last 50 years or so, is the questioning the life expectancy of putting exposed fiberglass in the airstream, in the plenums, etc. What about the fit and finish? You're aligning the internals of a duct. What if we have exposed edges? How does that behave with certain internal velocities, etc.? And duct cleaning, kind of a challenge if you have duct liner, but there are some measures that the duct liner manufacturers have employed to deal with that. But it does make it a bit of a challenge for your maintenance guys to deal with line duct. So saying that, within the silencer role, the way we've addressed it is when it's applicable, when it's suitable, we'll apply a standard absorptive silencer. Some of you folks may regularly do that. But in certain applications, healthcare facilities is the easy example. you want to protect the exposed fiberglass from the airstream, so we'll add some kind of polymer liner that goes between the perforated metal that's exposed to the airstream and the media film. So that does an excellent job of blocking the surfaces from touching each other, the airflow versus the acoustic medium. But then in 5% of the cases, 10% of the cases, a small minority of the cases, nevertheless, the system will be specified for no media whatsoever. That could be a food processing facility, a lab ventilation system, a hospital operating room, MRI clinic, those higher level, higher sensitive systems. They'll employ the reactive silencer that sort of touched on. Kitchen exhaust systems may employ a reactive silencer to decrease. Here are some characteristic curves of the same silencer. The yellow curve represents standard media film. The blue curve, which may not look blue where you're standing, but the blue dashed curve is the same silencer with the polymer protection using traditional polymer protection. There are other materials and techniques out there to achieve that type of protection. We happen to have our brochure on the table that we have some information with this, if this is something of interest to you, that deals with ways to avoid that performance degradation. You'll notice the big difference, the big delta between the yellow curve and the blue curve. That's using more traditional liners. Newer technologies are allowing us to kind of get rid of the gap, if you will, in performance. Now the green curve is a standard, is that same silencer geometry as the other two, but there's no media whatsoever, it's reactive. It looks like a lot of bad news, low performance, and that may be true. But it's the ultimate in terms of there's absolutely nothing in the airstream whatsoever. So when the system demands it, this is the way to go. But you can see where it's heading. It would probably require a longer attenuator to give you some performance and value. So if you will, as a placeholder, if you're dealing with an HVAC path, noise path, that you know is going to go into a space that does not allow for any kind of duct lining whatsoever, you may want to, especially at the early design stage, allow for a little more real estate. Maybe I think normally I can get away with a 5-footer here if I need a silencer at all, but because it's going into that lab space, I'm going to put a placeholder for a 10-footer or a 9-footer. And maybe when we're all done and when it's all said and done, we've done a path analysis, I don't really need 9 feet, but I've kind of protected myself because I know that I'm going to get something at that green curve. This is characteristic, of course. If it was an elbow silencer or some other configuration, the relationship would be slightly different. But the green curve, one last thing on reactive silencers, it's a tunable product. So this one happens to be tuning at 500 hertz, because I just arbitrarily pulled it out of the software selection tool. But if I had demanded more performance at 250 hertz, it would have taken a different configuration, tune chamber configuration, and perhaps it would have peaked at 250. So you can really drive it by what type of fan. So if it's a vane axial that's really screaming at 500 hertz, you could go with a silencer that has this profile. If it's a centrifugal that's maybe dominating at 125 or 250 hertz, it could be something else. So that ability doesn't exist with the other two products. Only a reactive silencer has that tunability. So a few slides here to kind of set the table for a final slide in this area of silencer characteristics. Let's take an arbitrary silencer and we hold the dimensions of this casing fixed. So it's 24 by 24 inches cross section, 5 feet long. Let's say for argument's sake, it actually is a 5 foot long comparison. And all we do is we manipulate the air passage through the silencer. These characteristic curves just show you what happens. The bottom bluish curve is for a high percentage open silencer, so it has a very, very large air gap, so very little pressure drop. And then we keep tightening up the gap, and we get the, okay, is that purple? I can't tell. We get the top curve. And you'll notice that by doing that, though, it appears we're getting some pretty good boost in attenuation broadband. But the pressure drop goes from 0.02 to 0.61. So if you can live with that, this technique is a very cost-effective way to get more attenuation out of the noise control package. But there's a certain point, and maybe it's way before you hit 0.61, there's a certain point where you're going to start getting concerned about your fan. And am I going to have to upsize the fan and just deal with the pressure loss of the silencer? We don't want to do that. You can avoid that. And one of the easy ways, quite frankly, a very cost-effective way, is just allow for a little more real estate in your duct system. So here, we're keeping the guts of the silencer fixed. In other words, the air passage size is fixed. And all we're doing is we're making it longer and longer. And the bottom curve is for a 3-footer, and it grows up to 12 feet. Top curve represents a 12-foot long attenuator. So all we're doing is we're adding a little friction loss. Not a big deal, but we are adding a little bit. And it goes from, in this case, it goes from 0.19 to 0.4. Not a big jump. And maybe you already notice a difference though. It's definitely another broadband boost, but the lines appear to be further spaced apart. And let's put them side by side, and if you assume that, you're correct. And we'll ask the question, what's the cost of low frequency performance? This vital low frequency performance I keep referring to. And maybe we have a centrifugal that's really causing you a problem at 125 hertz. So you want to come up with the most cost-effective way to deal with 125 hertz. On the left-hand side, we're tightening up the gap. On the right-hand side, we're simply making the attenuator a little longer. For every dB that you're trying to squeeze out of the graph on the left, the fan will have to work 0.06 inches more static for every decibel at 125 hertz. So I do a path analysis today, and I realize, oh, I'm 3 dB shy. If I keep everything fixed and just simply try to squeeze the gap a little bit more, the fan would have to work 0.18 more. And maybe that's the straw that broke the camel's back. You now have to upsize your fan or do something that you don't want to do with your fan. So there's no need for that. If you need the 3 additional dB, adding a little bit more length will only increase the pressure drop by 0.03 in this family of curves, of course. So a negligible increase in pressure drop. It comes with the price of a little bit more space in your system. So it really dovetails back to that whole discussion. Lay it in quick, lay it in early, talk to the team early, and this will not be problematic when you're at the 11th hour and it's going on for bid. But perhaps you're in the mechanical room and you have absolutely no room available. And you have an air handling unit and you have a damper, and you have 5 feet available. And the architect's not moving the wall. The wall's not going anywhere. What do you do? Well, if we were having this discussion on a live project, I would ask you, the follow-up question would be, okay, you can't move and you can't grow anymore in the axial direction. Can we increase the width or the height of the silencer to give you that low frequency performance you may require? And hopefully you would say yes to one of those 2 questions. Width or height. But here we're depicting a silencer that is growing. It starts off as a standard silencer. That's the blue curve at the bottom of the diamonds. And we're extending the width of the silencer. So you remember that rather dull image of that elbow silencer. Here we're looking at it graphically. We're adding 4 inches at a time. I believe it's 4 inches. Oh, yeah, 4 inches at a time. So it grows from standard silencer to 4 inches wider, 8 inches wider, 12 inches wider. You'll notice the significant boost we're getting in the low end. All 4 of these curves result in a pressure drop of 0.11 inches pressure drop at 1,000 feet per minute. The internals are manipulated to give you a particular pressure drop value that essentially are the same each and every time. So as far as the fan is concerned, this is the same silencer. It doesn't have to work any harder, but you're getting a boost. So this is what it could look like if it was an elbow attenuator. And you may ask, well, Emmanuel, why don't you build all your silencers like that? They're a little bit more costly, and it's more cost effective sometimes to just make it grow a little bit more, add a couple feet more of attenuator, you get a nice boost in the low end as shown earlier with that comparison to 125 hertz. That's usually the first way to go, the prime decision that you should make. But when you're really up against the wall for space, this is another tool that you have available to you, extended width or extended height. It's a little bit of good news when we're stuck in a mechanical room. Now, a lot of these topics that I've touched on are covered in these 2 books. They're aging well. They're again 15 to 20 years old. The Mark Schaefer book and the Chuck Epping and Warren Blazer book on the left-hand side. I really like the Application of Manufacturer's Sound Data, which is another publication from ASHRAE. Each chapter is devoted to a different piece of equipment, and it gives you a actually, it speaks to a lot of these issues that I'm talking about. What to look out for, what to consider in your system design. It's, I think, a mandatory read for a new engineer getting into the HVAC design world, but a real good refresher for someone who's been doing it for a long time. Okay, system effects. I'm gonna, in the interest of time, I'm gonna skip over fan system effects. There's probably a lot of experts in that area in the room as well. But I do want to touch on aerodynamic system effects when it comes to noise control. There's a table in the ASHRAE chapter. I believe the latest version, it has it as table 27. It describes pressure drop factors that we apply on silencers, but it could be other components as well. When that component is close to a duct fitting in our system, it's implied that we take the pressure drop value from the manufacturer's ratings and we multiply it by that pressure drop factor, and we now have a new net pressure drop based on system effects. But when I looked at this table many years ago, I immediately identified a few gaps, shall we say, in the information. Actually, before I handsome graphic here on the left-hand side, before I jump into that, there was this vagueness about the table as well. And keep in mind, it's been around for a long time, this table, so it's sort of the best we had at the time. So keep the context there. But it has this fairly wide range. It says, when a silencer, for example, is within 3 to 4 duct diameters from a miter elbow, I'm supposed to multiply the pressure drop of the silencer by 1.3. But intuitively, you know that, what if that silencer is right on top of that elbow? Is it actually the same as if it were 2 duct diameters away? Is that possible? It doesn't seem right. So here we have a depiction of a rectangular silencer on top of a miter elbow. There's an immediate observation. What makes a silencer unique is it accelerates the air as it enters, and it decelerates the air as it leaves. So it's not a straightforward duct fitting. It's not an elbow on top of an elbow. It's a device that's manipulating the airflow through the duct. So in fluid dynamics, you may recall a quantity called a Reynolds number. Kind of an important evaluation tool when we're dealing with HVAC aerodynamics, in particular silencer aerodynamics. The 3 key variables in a Reynolds number is the physical size of the air gap, which is with the duct diameter, but in this case for a silencer, it would be the gap of the silencer. So the tighter the gap, how it'll influence the Reynolds number accordingly. The velocity through that silencer, and the viscosity of air. That new symbol in the denominator stands for viscosity. Now, as mentioned at the very beginning, I'm interested in not just commercial HVAC noise control, do a lot of industrial and power plant noise control. The gas turbine silencers have exhaust temperatures of 800 to 1200 degrees Fahrenheit. So air viscosity is kind of a fluid viscosity, is kind of a big deal in that area, that it differs dramatically from standard air conditions. So this is kind of an important quantity at VAW in terms of how we evaluate system effects. So there's that aspect, so the fluid dynamics aspect of this. But let's go further though. Earlier I showed a single air passage silencer, but that could easily be a 2 air passage silencer. They come in various forms and configurations. It could be a 3 air passage silencer. So there's no distinguishing feature in that table, in the ASHRAE table, unfortunately, that deals with these issues, if you will. So it's important to maybe lean on your noise control manufacturer to account for these very basic yet essential aerodynamic effects. And one of the ways you could do this is kind of a combination, is my opinion, of course, between physical lab testing and fluid dynamics modeling. Okay, so here, we got time now. 8 minutes? Okay, I'm going to dive right into the case study because just a few pretty pictures here. Let's just enjoy. Okay. All right, case study. We'll end with 4 or 5 slides here. Here we have a rooftop unit. And in most of these applications, we need to consider at least one ductborne path and one breakout noise path for every critical unit. So it's a simultaneous calculation, a related calculation, but 2 different ones nevertheless. And here's the philosophy part of it, as advertised. We want to try to apply the noise controls as close to the source as possible. in every case, whether it's a genset, a condenser, what we want to kill the noise as close to the source as possible to not allow it to propagate into our building and create what's called, sometimes called secondary noise paths. So what results when you apply this philosophy, we'll call it that, usually the noise controls end up right under the rooftop unit, right there. Right, you have the rooftop curb, if you have one. The noise control needs to go right underneath that, kill it, like I said, right at the source. Or right within the mechanical room, right on the fan if it's warranted, or even at a wall partition if we're trying to protect for speech privacy for room to room. If you employ this, and I'm going to demonstrate it in this case study, of course, you're going to relieve the design specialists of having to deal with some very big problems later in their system. If you knock out the noise as close to the source as possible, it's going to make their lives easier, and quite frankly, challenge the noise control team to come up with a solution that works. Because time and time again, it will be the most cost-effective when the system is built up. So I mentioned elbow silencers a few times already. When we're dealing with rooftop units, for example, and this is a case study on a rooftop unit, quite often the air turns immediately underneath the air handling unit for a variety of reasons. So if we're going to employ that philosophy, we typically have to go with an elbow silencer. The neat thing, or the unique aspect of an elbow silencer, is as the length of the attenuator grows, the pressure drop does not increase at the same rate as a rectangular silencer. And the reason for this is a very basic aerodynamic phenomenon that as the tail of an elbow increases in length by a foot, by 2 feet, by 4 feet, the pressure drop will actually benefit from more and more regain, static regain, within this system, within this black box. So depicted on the screen, for again characteristic curves, is starting at 3 feet in length. We increase the silencer length of an elbow, that's the red curve, and a rectangular silencer. And you notice a big difference in the slope. How could you leverage this? You benefit, not pound for pound, for dB, the elbow silencer is going to be a much more efficient selection for this reason, when it gets very, very long, if it needs to get very, very long. But here's a real life scenario. You perhaps laid in or selected a 7-foot long elbow silencer. At the very early stages, you felt you did the prudent thing, and the mechanical equipment went from being 90 dB to 100 dB. Because there's been some changes. We're at the 11th hour. We have to get our work done. And we have some good news and bad news. We're almost there, but the bad news is the air handler is now 10 dB noisier. What are you going to do? Well, you did the right thing. You laid in, you selected an elbow silencer right from the get-go. This implies that if you need to increase the length, the center line length of that elbow silencer, assuming you have the room, you're not going to pay a big pressure drop penalty. If you don't pay a big pressure drop penalty, perhaps you're safe and you don't have to change the fans one more time. And typically get changed several times in the life cycle of any project. But likely the elbow silencer is not going to be the cause of yet another change. So there's some good news there, something you could leverage, if you will. Okay, back to the rooftop unit. This is a clip out of an actual manufacturer specification sheet. Really concise and clear. But I'm going to focus in on the outlet sound levels because we're looking at discharge noise over an occupied space. You'll see a graphic of it in a second. But I'd like to do a quick dinner napkin calculation, shall we, of the low frequency noise, just to see if I was evaluating this air handling unit, can a dinner napkin calculation, quick calculation, tell me whether or not I'm in trouble if I go with this selection? Well, I'll do 2 calculations that we noted earlier. I'll compare the DBC versus the DBA. So that's a logarithmic calculation. Feel free to look that up. Again, I didn't cover the arithmetic tonight, but it's available in the literature. The overall DBA is actually given by the manufacturer. But by the way, if they didn't give you the DBA level, you can just use those octave band levels and calculate the overall DBA yourself. It happens to be 99. I take the same octave band readings and I calculate the DBC. And again, according to that standard, I want to know what the difference is. The difference is only 9 dB. So it seems okay. Maybe I'm on to something here. I'll avoid a problem. But I'm also going to, in the spirit of doing a quick check, you haven't seen the graphic yet, but believe me, the the noise path, it results in a room that's very, very close to the RTU, very, very close. So knowing this, you can do a quick budget of, call it roughly 10 dB acoustical losses due to the ductwork. That includes a little bit of ductwork and an elbow effect, a sheet metal elbow. That'll come out to roughly 10 dB in the low frequency range. And a room effect, getting back to the simplicity of the ASHRAE algorithms, at 63 hertz, it's usually plus minus a dB or two, it's usually around 12 dB. So I just want to get close here. It's acoustics horseshoes. That results in 22 dB loss, ballpark, and I'm at 80. And what did we say earlier that if it's above 70, we should watch out. Maybe we're introducing a little bit too much low frequency sound pressure in the space. So be careful. So perhaps this would be a trigger for calling your expert and asking him or her to look at it a little more carefully, because your quick evaluation did not produce promising results. Here's the situation of the unit. We're only going to look at the supply air duct, which is depicted on the right-hand side. This is an artistic rendering. We're going to evaluate breakup noise immediately below the unit and the duct-borne noise at an adjacent room. And for simplicity, we're going to shoot for NC35. Let's say it's kind of typical. Skip this, some talking points on the fan specs, but not too important on this duct path analysis. We're going to evaluate a few different scenarios. What if we consider line ducting? Then we can consider the same duct system layout, and we consider an elbow silencer right under the unit. And we'll do a scenario with and without a ceiling. And we can see the impacts of just a simple change like that. And that's another 11th hour thing, that could, a curveball that can be thrown at you where you thought you had acoustic ceiling tile and it was taken away. It could create some problems. Here's the duct path again calculation. We'll skip over that. Let's get right to the results of those various scenarios. In the center are the results of the duct breakout path. The first two are the line duct scenario and the elbow silencer scenario. Both fabricated at a 22 gauge with a ceiling tile. So let's ignore everything below. That's the no ceiling scenario. If we go over to breakout noise, we notice that if we only use standard 22 gauge duct with internal lining, perhaps it's intuitive when you saw those big numbers that we saw earlier, 100, was it 100 dB in the low end? That's pretty substantial sound power. That resulted in NC39, and remember we're shooting for NC35. So it does not meet the criteria. The elbow silencer with 22 gauge and a ceiling tile hits NC33, so we're good for breakout noise in that scenario. Going over to the duct-borne path, I'll read it out for the folks that can't see it from their position. The line duct scenario, the very first row, that also results in NC35. But in my calculation, I had to keep increasing the duct length out to 50 feet. So 40 feet didn't work, 35 feet didn't work. I had to keep increasing the line duct length until I hit 50. And then and only then did I exactly hit NC35 with no margin. It's just right there. So if you have the space, you can pull it off. 50 feet is fairly substantial in this particular case. Again, it's driven by all that energy, that sound energy you saw on the low end earlier. And again, the silencer can be anything we want it to be, I suppose, as far as physical size. Again, I kept, not the software actually, keeps increasing the length of the elbow silencer until it hits the criteria. In this case, it resulted with a 7-foot long attenuator. So we avoided the 50 feet of line duct by going with it. And by the way, a lined elbow fitting, because the very first row here is lined elbow fitting and then a run of line duct. We've been able to eliminate that with a 7-foot long attenuator. And here's, if you will, the real added bonus, a critical issue here, breakout noise. Going with the line duct, now we can talk about the no ceiling condition. You remember before, the line duct failed even with the ceiling. It's disastrous with a no ceiling condition. It's NC47. So here's a potential scenario I hope none of you encounter. If you missed this detail and the system was fired up and people were just screaming and yelling about the noise level in the room immediately below the air handler, it would be extraordinarily costly if you had a note ceiling situation and it resulted in NC47. Because not only would you have to add potentially, one of the ways could be, well, why don't I lag the duct? That could be done. It could be done with various techniques, adding mass to the walls, etc. But it's exposed ductwork. So there's certain things you can and can't get away with in that situation. And by one example, it can't be ugly, shall I say. It has to be a fairly attractive looking duct lighting feature. So a big, big problem if this was a detail that was missed for breakout noise. Now, a standard 22 gauge auto silencer also fails in this scenario. It hits NC41 with no ceiling. You actually have to bump the casing gauge a little, and when you hit in your selection tool, when it manipulates at the 16 gauge, it's fine, it's NC35. 16 gauge is a little bit of a bump up from 22, but you now hit the criteria immediately below the unit. I'm probably a little short on time here, so I'm just going to end it with that. Thanks for your time and your attention.
So if anyone has any questions for Emmanuel, just ask. Any questions? I'm sure he's happy to answer any questions that the booth
Just hang on here for a while.
you want to ask him personally. Thank you very much for coming to the chapter. Gift here for you. Just peek out. Shake your hand. Thank you very much. Great. Well, thank you, Emmanuel, and thank you, everybody. Just a couple of things before we let you all loose. Sorry for keeping you a little late here. So first thing, I guess, we'll be sending out an evaluation form. So we do value your feedback. We want to hear what you have to think of the meeting. There's several sections in there, so please fill it out. Also, if you want to comment on the buffet versus the regular meals that we have here, let us know as well. Next meeting, we'll be back here in May. It'll be Dan Gosselin from BGIS. He'll be talking about some of their initiatives and PSPC's initiatives in low carbon and low energy buildings. So look forward to seeing you all there. Thanks again for coming. Thanks to Centurion again for great service, and we'll see you all at the next meeting.